Welcome again. In this lecture, I will give an example of a Nyquist plot and design a controller. We will also verify the controller. So here is the problem statement. Draw the Nyquist plot for this transfer function g of z given by 1 over z into z minus 1. So here is the plot C1, and we don't want C1 to go through a pole or a 0. We have chosen C1 to be a unit circle. We have also indicated by cross the poles that this G has. So G has a pole at z equals 0 and another one at z equals 1. We have chosen unit circle as C1. So we have made an indentation here so that C1 will not go through a pole. Recall that this is a requirement of the Cauchy's principle. So C1 should not go through pole or 0. We indented it with a semicircle of radius going to 0. This is a very small semicircle. Inside the C1 curve, all the poles are here. So outside there is none. So we say that the number of unstable poles that this plant has is 0, that is capital P equals 0. So let us draw the Nyquist plot. We will first evaluate B by A along main C1. The C1 has two parts, one is this main C1, the other one is the small semicircle. So we will first do it along A, B, D, E. For that we will substitute z equals exponential j omega. This is on the main circle. When I substitute z equals exponential j omega, I get this. Let us simplify this. What I have done is I have pulled out exponential half j omega outside. So I get exponential 3 by 2 times j omega here, and I get exponential minus half j omega here, and I can write this as this factor goes to the numerator, and what is inside the bracket becomes 2 sine half omega using Euler's formula. Then I apply Euler's formula here to the numerator to get this cos of 3 by 2 omega minus j times sine of 3 by 2 omega. I get this here. Now we will simplify this, split this into real and imaginary parts. Real part comes from here. You have j into j minus 1. So you have second minus sign, third minus sign, overall you have 1 minus sign, and sine of 3 by 2 omega divided by 2 sine half omega. Similarly, the first term gives rise to the imaginary part. So the transfer function that we derived in the previous slide is this. This is applicable for the main part of the C1 curve. We will first evaluate at the point A. A corresponds to omega equals 180. So you can see that here it becomes sine of 270. So that is like sine of 90. There will be a non-zero term here. Here it will be a cos 90 term, so this will become 0. So it is easy to check that you get g equals 0.5. This term will give rise to 0.5. So let us plot this point A on the next curve. So imaginary versus real, A corresponds to 0.5. That is, I evaluated this transfer function at A, plotted the imaginary versus real, and I got this point. Now let us do this for B. I have chosen B to be at omega equals 120. Let us substitute this 120 in this expression. I get this term. You can check that at every omega I have put 120. Let us simplify this. So this is 3 times 60, 180, this is 60. Similarly for the imaginary part, and when I evaluate this, sine of 180 is 0, whereas cos of 180 is minus 1, and you have a minus sign here. So it becomes plus j times 1 over this whole thing. So it is easy to check that this corresponds to 0.5774 j. The real part is 0, the imaginary part turns out to be 1 by root 3, and 1 by root 3 is 0.5774. Okay, this is point, this corresponds to point B. So let us plot this, it should be somewhere here, that is point B. So I have connected A and B. So let me start with that curve. So the transfer function is given by whatever we had in the previous slide. Now let us evaluate this at the point D, where I will choose omega to be 60 degrees, and let me substitute for 60. This becomes cos of 90 and hence 0. So I have this here. This becomes sine of 90, I get 1 here, and this is sine of half omega, that is sine of 30, which is half. When I simplify this, I get this as minus 1. So if I evaluate this at D, I will get G equals minus 1, it is somewhere here. So let me plot it and connect it. So I have got this D. Now let me do this for E. At the point E, omega goes to 0. So let us substitute omega equals 0 here. I get sine of 0 divided by sine of 0. So I get 0 by 0 form. Cos of 0 is 1, 1 by 0 is infinity. So I write this as minus j times infinity. So I have to resolve this 0 by 0. So what do? I use the L'Hopital's rule. Here is the L'Hopital's rule. I have to differentiate both the numerator and denominator with respect to omega. So I differentiate and I get this. Now let me substitute omega equals 0. You see that cos terms result in 1. So this is minus 3 by 2 minus j infinity. So this will go somewhere here. It is minus 3 by 2 here, and it is infinity in this y direction. So here is the plot. So let me start with that plot, and now we have to take it along the small semicircle. We have to evaluate this G along the small semicircle, and we have got this small semicircle by indenting around the point 1, 0. So this is a semicircle with center at 1, 0 and radius goes to epsilon. So I can write this as z equals 1 plus epsilon j phi, where phi starts from plus 90, it goes through 0 to minus 90. You should always represent this curve with a minimum of 3 points. Here it starts at 90, goes through 0 and minus 90. If you remember, if you forget to include this 0 degree, that is the intermediate point, you could make mistake. You should always remember to include the intermediate point. So let us substitute for z in this expression, G evaluated at 1 plus exponential j omega times epsilon. When I substitute in the place of z this whole thing, I get this, and when I subtract 1, I get this second term. Let us simplify this. What I have done is I have taken this term to the numerator, so it becomes epsilon to the power minus 1. The second term becomes exponential minus j times phi. The second term is retained as it is. Now let epsilon go to 0. When epsilon goes to 0, this becomes infinity. I can ignore this term, so you get 1. I do not have to write that 1. So it is infinity times exponential minus j phi as epsilon goes to 0. So you can see that it is also a circle of radius infinity. It goes from minus 90 degrees because we started with plus 90 with plus j phi here. Here we have minus j phi, so it starts from minus 90. This 90 becomes minus 90 because of this minus sign. 0 remains 0, minus 90 becomes plus 90 with infinite radius. So this is a circle of infinite radius, but it is only a semicircle. It starts at minus 90 and concludes at plus 90. So it starts at minus 90. Remember, this point is minus 90 because this distance is infinity. We cannot write infinity in this paper, so we have indicated it E going to infinity. So this circle of infinite radius starts here, goes through 0 and then concludes at plus 90. So here it is, here is the circle. We can now complete the plot. We can complete the plot by connecting all the other points, and notice that it is symmetric about the real axis. This is a Nyquist plot we obtained. This is the transfer function g, and now we will determine controller from this Nyquist plot. P is the number of unstable poles of g, and P is equal to 0 because there is no pole outside the C1 curve because of the way we have indented this small semicircle. Recall the Nyquist condition. C4, this is C4 curve, it should encircle the minus 1 by k comma 0 point how many times? Capital P times. That is, for stability it should not encircle because P is equal to 0. Because P is equal to 0, this C4 should not encircle minus 1 by k comma 0 point. Okay. C4 should not encircle minus 1 by k comma 0 as P equals 0. Now when is that possible? Supposing I have minus 1 by k comma 0 point somewhere here, then we will see that this point is encircled once. If I put it here, it will be encircled twice. Both of them will violate this condition that it should not encircle. As a result, it follows that this minus 1 by k comma 0 point should be to the left of this point D, should be somewhere here. So if minus 1 by k is to the left of minus 1 comma 0 point, the closed loop system is stable. So we get the condition that minus 1 by k should be less than minus 1 but greater than minus infinity. In other words, it is in this to the point to the left of the point D. When I change the sign, the directions of this comparator operator changes. So let me multiply throughout by minus 1, greater than sign becomes less than. I get this condition. I will split this as 1 less than 1 by k and 1 by k less than infinity. So the first condition says k is less than 1, and the second condition gives k greater than 0, or I get 1 greater than k greater than 0 from here. So this is the condition you have to remember. For stability, k has to lie between 0 and 1. The plant is given by g equals 1 over z into z minus 1. We have found the closed loop system to be stable for k in the range 0 to 1. Let us see what happens when we evaluate for k equals 1. So let us substitute k equals 1 in this equation. So I have to substitute k equals 1. It becomes z into z minus 1 plus k equals 0. For k equals 1, the roots are, you can verify this, half plus minus j into root 3 by 2. I would want you to pause this video and verify this value. What is the magnitude of this? The magnitude is 1 because this will give 1/4, this will give 3/4, together it is 1. Because it is of magnitude 1, this point lies on the unit circle. For k equals 1, the roots are on the unit circle. For any larger value of k, the root will be outside the unit circle. That is roots of this equation. So poles are on the unit circle for k equals 1. For k greater than 1, poles are outside the unit circle, making the system unstable. As a result, we have verified that this system is indeed stable for k in the range 0 to 1, and for k greater than 1, the system is unstable. We have verified the results of the Nyquist plot. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.